Hello people, welcome back to my channel. The topic for today's video is the backpropagation algorithm. So in the last video we saw what was the chain rule. So that is the basis for understanding this particular video. So if you haven't watched that video, so make sure that you check that video first before you watch this. So I'll just put the link in the description so you check that out. So basically when we want to just backtrack to each individual unit in a different layer in our neural network, we mainly use the backpropagation algorithm, and the updation of the weights is performed mainly by the gradient descent algorithm. So we essentially know that as our weight, which is the new weight, is given by the old weight minus we have some parameter, say lambda, and we differentiate the loss function with respect to the weights. So this is how our gradient descent algorithm says. So this is the weight updation at each unit takes place. So this lambda is nothing but your learning rate, and which controls the speed of convergence. So whenever you have a function like this, so if you want to just go down, that is against the direction of this, so in order to take small baby steps, you just descend down the valley. So that's why we mainly use this particular negative sign to just come down. So now essentially what we have is we have our cost function, that is j, which is function of both weight as well as the bias. So our free parameters, that is in loss function, is mainly revolved around these two parameters, that is the weights and the biases. So we need to adjust this, which we have assigned randomly. So that is our major goal. So how do we write this particular equation? So this is given by, say you have minus 1 upon m, where m is a number of training examples. You have I runs from 1 to m log of y and y cap, that is the loss function. So the cost between the weights and the biases is expressed in terms of the loss function, that is y and y predicted. Now let us try to expand this, so which becomes minus 1 upon m summation I runs from 1 to m, that is this becomes y log y cap plus 1 minus y log 1 minus y cap. So this is how our loss function looks like in terms of y and y predicted, that is the actual and the predicted value. So now we know our chain rule from our previous video. So what we try to do is we try to achieve, that is dou L by dou W. So we try to update the weights in this particular scenario, but if you look the cost function, that is this particular equation does not have anything in W so that we can differentiate. So essentially we will try to apply the chain rule and we'll see how we can represent this. So first of all, in our neural network, so say for instance we have x1, x2, x3. Consider this scenario and you have some weights and connections like this. Finally you get the y cap. So you have one layer here, so this is your output layer, this is your hidden layer, and this is your input layer. So now with respect to the loss function, you need to go back and adjust the weights. So weights are essentially present at this particular portion. So here you have, say, weights at the first layer, and here you have weights at the second layer. So how do you represent this? So first of all, the loss function will be dependent on your y cap, that is the predicted. So from the predicted we start. So from this portion, that is from the right hand side, we just backtrack to the left hand side. Now this y predicted is a function of z. So since we know that is our z is w1 x1 plus w2 x2 up till you have wn xn plus b. So this y predicted, that is y cap, So y cap is essentially, you can say, if you use a sigmoid function here, that is for calculation, you have 1 upon 1 plus e raised to minus z. So you can essentially differentiate this. Why? Because you have a z in this particular term, and then finally your dz can be differentiated with respect to w. So that is, z is a function of weights and your inputs. So this is essentially how our chain rule is that we are going to use in this particular backpropagation algorithm. So let us compute each of the terms one by one. So essentially, say take we have this particular equation, so which is nothing but we'll just consider for minus, we'll just not average this, that is the total loss function. This is just the average of the loss function. We'll not take the average, instead we'll take the normal loss. So just consider minus, and say this is nothing but your dou L by dou y cap. So y cap is your final function. So how do you differentiate this? So for that, say you have minus and you have y log y cap. I'll just write this here so that it becomes easier. So this is our function. Now we need to differentiate this. How do we differentiate this? Instead, I'll write it as more clearly. This is your L. Now dou L by dou y cap. So that is y. This is not, this particular y is not a function of y cap. You will keep the y as it is. The derivative for that is dou L by dou y cap. In this is the derivative of log y cap is 1 upon y cap. So you will just write this, and 1 minus y. For this you have 1 upon 1 minus y cap. Now derivative of minus y cap. So which is a function of y cap? That is nothing but your minus 1. So this completes your derivative with respect to the chain rule. So now our final dou L by dou y cap becomes, we'll just consolidate this. So this is nothing but your y upon y cap, which has a negative sign. You have this negative, when it goes inside, this becomes negative, and with this it becomes positive. So you can rearrange this as 1 minus y upon 1 minus y cap, and in this portion you have y upon y cap. So we have just occurred, we got this, that is the very first term in this particular chain rule. Now we need to differentiate y cap, that is our output. So essentially our output is nothing but your this function, that is for the logistic regression, that is a sigmoid. So if you can see, you can essentially differentiate this very much easily with respect to dou z. So you have dou y cap by dou z. So if you just look into this expression, what you can see is either you can apply two ways. So you can do in either of the two ways. So you can use the u by v rule for differentiation, or you can just normally consider this as expression as 1 by x. So derivative of this is minus 1 by x square. So for simplicity, we'll just consider this as 1 by x. So if you treat this as 1 by x, so you have minus 1 by x square, and then you need to take the derivative of this denominator, that is this part. So that becomes minus e raised to minus z. So derivative of e raised to x is nothing but e raised to x, but you have this z as well, that is minus z. So you need to take derivative of minus z, which is nothing but a minus 1. So that's why we are taking this minus. So now what we get is e raised to, so this negative just cancels out here. So 1 plus e raised to minus z. So now we need to adjust this particular numerator such that we can reduce this. So what we do is we add a +1 and -1. So what our equation just reduces to is 1 plus e raised to minus z, this is a square, upon 1 plus e raised to minus z square minus 1 upon 1 plus e raised to minus z square. So now what we do is we'll just rearrange that and we'll just substitute. So our dou y cap by dou z, what we can achieve is, say this numerator and denominator are same, so if you just cancel out one term, so you are left with 1 upon 1 plus e raised to minus z. So one power gets lost here, and that is nothing but your 1 upon 1 plus e raised to minus z square. So what you can do is, this is nothing but your y cap, and this is your y cap square. So y cap minus y cap square, or you can take this as y cap common, you have 1 minus y cap, or you can just write this as the output. So this is the output OL, what we get here is as the OL output layer, 1 minus OL. So you can essentially write your sigmoid function, that is whenever we use this, as output 1 minus output. So that is nothing but this. So now you have the two terms from the chain rule. Now we have to take the one more, that is our final dou z by dou w. So dou z by dou w is nothing but your z is wx plus b. So if you differentiate this, b is a constant, so that becomes 0. Then for w you have left with x. So our final dou L by dou W became, so you have this particular quantity, so this is the first quantity, 1 minus y cap minus y by y cap. This is first quantity. Second quantity is this, that is y cap 1 minus y cap, and finally you have x. So what we try to do is, we try to just minimize this or see if we can optimize this particular thing. So what we do is we just cross multiply, so that is y cap 1 minus y into 1 minus y cap divided by y cap 1 minus y cap into y cap 1 minus y cap, and you have a x here. So you can see these two terms just get cancelled out, and what you are left with is you have this numerator part and with this x. So if I open this bracket, you have y cap minus y cap minus y plus y cap, and with this you have x. So if you see, these two gets cancelled out, and what you are left with is y cap minus y into x. So this, what we have done is a general representation of how we can differentiate our loss function with respect to weights. So now you can see, if you have such particular kind of network, if you look, you have 2 cross 3, that is 6 number of weights. So for each of the weights you have to do this much amount of computation for updation of this gradient descent, or by using the chain rule. So this was for your particular individual weight. Now for biases, that is nothing but your dou L by dou B. So this part all remains the same, but just when you come at this particular point, that is here, when you just differentiate with respect to B, this part and x remains the constant. For b you have 1 left, so that is nothing but your 1. So if you have dou L by dou B, if you take the differentiative of this, what you will be left with is y cap minus y, and you have a 1, that is derivative of B, that is nothing but 1. So you have these two equations. So that's where how you differentiated the loss function with respect to both your weights as well as the biases. Now what we'll do is we'll do an activity of having two different neurons, that is two different layers, and we'll take one training example and we'll see how we can represent this in matrix form so that it becomes easier for our vectorization computations. So now what we have is we'll take a setup of having two different neurons and we will have one training example, and we'll see how we can use the backpropagation algorithm or use the chain rule in order for our computation. So say we have two neurons here or two units, we get the final y predicted as the loss y cap, and then you have weights here, say one training example x1, and then you have some weights here as well. So whatever computation goes here, that is the linear summation, and whatever you get here, that is, say we call it as A1, and here what you get is Z2. So where Z2 gets input, that is A1 serves as the input for Z2 and it gets multiplied with this W2, and with sigmoid it gives you A2. So now what we try to do is we'll just use the chain rule that we have seen in the last video or the last clip. So we have dou L by dou W1. So how do you take the derivative of this, or if you want to just backtrack by using the chain rule, how will you go? So dou L by dou y cap, that is you go this way. Dou y cap by dou y cap is a function of what? That is dou Z2. Then dou Z2 function of A1. So we differentiate with dou A1, and dou A1 is a function of dou Z1, and now dou Z1 is a function of dou W1. So you can see how chain rule can be applied across the different layers or for this particular unit. So this is just a small fraction of what our neural network is. So we can consider n number of different such connections happening inside a large neural network, say like convolutional neural network or deep neural networks. So you can just replace this y cap by A2, so that's not a big deal. So just for our understanding, we have just started from y cap, but gradually your A2 is the output from this particular neuron, so you would be coming to this and then you just backtrack. So y cap is nothing but your net output that you get after all the processing from different layers. So now what we do is we'll just move this particular structure neural network to some higher structure. Say we have this setup, say we have 3 inputs and we have 2 neurons at this particular portion, and say we have connections here. So you have connectivities like this, and you have final output y cap, and then you have 2 portions here. So now what we do is we'll just label this particular equations, and we'll just rename this. So whatever we get here, that is we have the Z1, that is the linear function at this particular layer, that is the very first layer, and then what we have is we have the output, that is A1 from the first layer, that is from this unit, and similarly you have Z2 from the first layer and you have A2 from the first layer. Now for this, what we represent this as Z2 Z1 of the second layer and the output is A1 from the second layer, since we have only one neuron that is sitting in this particular portion, or say this is the output layer. So now what we do is we'll just try to differentiate this particular equation, or we'll just say like how we can take the derivative and how this particular path is followed. So say our loss function, so this, consider this as A. So where you have individual layers, I'll just call this as A net, or say A. Anyways, so now what we do is we take the derivative of with respect to dou 11, dou L by dou 11. And before that, if we remember in our weight matrix video, we have told that we are representing our weights in form of some matrix so that our computations becomes easier. So how many weight matrices or weight units you can have here? So that is nothing but you have 2 cross 3, that is 2 rows and 3 columns. So that is W11, W12, W13, W21, W22, W23. And similarly for in this particular network, that is the second weight, you have that is 1 cross 2, that is you have W11 and W12. So now what our major goal is to just minimize this particular weight matrix in a much differentiable form by using the chain rule, so that our computations becomes much more simpler. So we try to optimize this particular functionality by computation as much we can. So now how do we just go back from this particular loss function to the individual weights? Now you can consider this as a complicated network. Now you can see how many paths are there, that is the blue connectivities. So we'll just see how we can just go to this particular portion. So now what we start from is this particular layer. So what we have is dou A1 and 2. So we start from this particular portion. Then what we have is dou A1 from the second layer. We go to its linear function. So this part, that is sigma and non-linear part. Now dou Z1 from the second layer. So from the second layer, now we have 2 ways to go, either this way or this way. So you have to choose any one path. So but our W11 is from this particular portion. So essentially we would be taking, that is this portion, that is Z is a function of this output, and then you have dou A11, and then you have dou Z11, and finally from dou Z11 you will reach dou W11 from the first layer. So how you backtrack this? Basically from the second layer you went to first layer. So now this particular routing of from where to where you have to go, that becomes a particular difficult activity. So now similarly for dou W12, W13, you will write the same equations. So essentially what we do is we take a matrix, something like you have a differentiated weight matrix. So what you do is differentiated weight matrix at the very first layer. So instead we keep this, what we do is we take the differentiated form, that is you take dou L by dou W11, dou L by dou W12, dou L by dou W13, dou L by dou W21, dou L by dou W22, dou L by dou W23. So we have nothing changed in this, but instead we have tried to represent in some compact representation. So we are keeping some minute values of weights so that our updation becomes easier. And similarly we do the same justice with our second matrix, that is dou L by dou W11, dou L by dou W12. So this dimension does not changes, but instead we try to represent in much more simpler form, so that it becomes easier for our computation. So well, this is all regarding the backpropagation algorithm, which is the most important rule when you want to update the weights in a particular neural network with the help of chain rule. So if you know what is chain rule, then it becomes easier for calculating the backpropagation. So well, that was all regarding the backpropagation algorithm in deep learning. So hope you guys enjoyed this video. If you found educated watching this video, please do like, share, comment, and if you are new to this channel, please consider subscribing. Thank you very much for watching this video.